In modern textile manufacturing, energy consumption is a critical challenge. The dyeing and finishing stages, especially the heat-setting process, account for a massive portion of a factory's energy use. At the heart of this process is the Stenter setting machine, or SSM, a high-energy machine that dries, stretches, and stabilizes fabric using heated chambers and airflow. Traditionally, operators have relied on experience to set temperatures, fan speeds, and motor speeds. But this approach leads to inconsistency, both in product quality and energy waste. The goal? To optimize control parameters in real time, reducing electricity use without compromising fabric quality. And to do that, we need accurate predictive models. But here's the catch. Building such models requires vast amounts of historical data. In practice, that's expensive and often impossible, especially when launching new production lines with limited sensor coverage. So how do we build accurate models with little data? Enter Ensemble Deep Transfer Learning, or EDTL, a novel framework that combines the power of deep neural networks with transfer learning and ensemble methods to deliver high accuracy, even when data is scarce. Let's unpack this. Why traditional models fall short. Deep neural networks are great at modeling complex, nonlinear systems like drying processes. They can predict moisture content, fabric width, weight, and energy consumption, key variables in textile production. But they have a major weakness. They assume training and test data come from the same distribution. In real factories, that's rarely true. Different machines, different sensor configurations, different fabric types, these create domain shifts. A model trained on one production line often fails when applied to another. And if you're starting fresh on a new line with only a few weeks of data, you're stuck. Even worse, most models focus on just one output, like moisture content, ignoring the bigger picture. We need multi-target prediction, estimating energy use, fabric weight, width, and moisture simultaneously, so we can optimize for both efficiency and quality. The solution, Ensemble Deep Transfer Learning. EDTL tackles these challenges through a three-stage workflow. First, pre-train a DNN on a data-rich production line, say line B or A2, where historical data is abundant. This pre-trained model learns generalizable features, how temperature affects drying, how airflow influences moisture loss, and how fabric type impacts energy demand. Then, when deploying to a new data-limited line, like line A1, we don't start from scratch. Instead, we transfer knowledge via deep transfer learning. But here's the innovation. We don't just fine-tune one model. We build an ensemble of them. Each base model in the ensemble inherits the pre-trained weights, but we fine-tune different layers. One model fine-tunes only the second hidden layer, another the third, and so on. One model even fine-tunes all layers. This creates diverse learners, each capturing slightly different patterns from the target domain. Why does diversity matter? Because it reduces overfitting. If one model gets misled by noisy or anomalous sensor data, others compensate. The ensemble learns to average out errors, like a committee of experts voting on the best prediction. Finally, we use stacking regression to combine these base models. A meta-learner, specifically support vector regression, takes the outputs of all base models and generates the final prediction. SVR is ideal here. It handles nonlinearity, resists overfitting via regularization, and guarantees a globally optimal solution. And crucially, EDTL doesn't require complete time series data. It can handle missing or corrupted sensor readings, common in industrial settings due to communication failures or aging equipment. The ensemble structure absorbs this noise, making the system robust. Real-world results, data efficiency, accuracy, and robustness. We tested EDTL on real-world data from 3 textile production lines. Line A2 and B served as source domains, rich in data. Line A1 was the target domain, with only 20% to 40% of the data available. Compared to a standard DNN trained from scratch, direct learning, EDTL reduced prediction errors by 5.66% in key metrics like electricity consumption and fabric width. Even with just 20% of the data, EDTL outperformed models trained on full datasets. Transfer learning alone helped, but EDTL was consistently superior, especially when the pre-trained model was suboptimal. For example, when transferring from a lower quality source line, B, standard transfer learning suffered from negative transfer, where poor source knowledge hurt target performance. But EDTL recovered. Its ensemble smoothed out the noise, delivering predictions nearly as accurate as those from a high-quality source. And when we introduced synthetic sensor anomalies, simulating real-world issues like drifting temperature readings, EDTL again shined. While other models saw performance drop by over 20%, EDTL degraded by less than 10%. Its robustness came from diverse knowledge sources and stabilizing ensemble averaging. Why this matters beyond textiles? This isn't just about saving energy in fabric factories. The core idea, learn once, apply everywhere, stay accurate with little data, has broad implications. In power grids, EDTL could enable accurate demand forecasting, even in regions with sparse historical data. In chemical processing, it could optimize reactions across different plant configurations. In food production, it could maintain quality across shifts and facilities, without retraining from scratch. The future of smart manufacturing isn't just more data, it's smarter models that learn from experience, adapt to change, and thrive under constraints. Final thoughts. EDTL proves that you don't need massive datasets to build powerful predictive systems. By combining deep transfer learning with diverse ensemble learning and feature alignment, we create models that are not only more accurate, but also more robust, scalable, and cost-effective. It's a leap toward truly adaptive, energy-efficient manufacturing, one where every new production line can be optimized from day one, not months later. If you're working in industrial AI, process optimization, or smart manufacturing, this is a framework worth exploring. Because in the age of Industry 4, the most valuable resource isn't data. It's knowledge that transfers, scales, and survives.